In this ShearMap application example, we're going to look at a Honeycomb Composite panel with 3 fabricated delamination patches of varying sizes, where the smallest one is just at 1 cell. This is a similar type of material as the European Space Agency wants to use on the black upper stage of their new Ariane rockets, as it is both more durable and lighter than metal. However, when we participated in ESA's benchmark tests on non-contact, non-destructive testing on advanced composites, we learned that due to the structure of these types of materials, it is hard to verify their integrity using traditional NDT methods. We start off by looking at the surface wave patterns from some single frequencies. First, we look at 40 kHz, where we see one patch where the surface wave patterns change. This is because the stiffness of the structure changes at the delaminated area, which again causes the wavelength of the surface waves to change. At 60 kHz, we see the same at a smaller area, and at 80 kHz, we start to pick up the same effect for the single-cell delamination. Finally, we run our patented damage detection scan from 50 to 90 kHz using 75 steps to demonstrate how quickly these defects can be identified in real time. This is a good time to note that while the ShearMap is designed with vibration excitation in mind, and we use a piezo as the excitation source in this example, it can obviously also be used with thermal and vacuum loads. Also, because the ShearMap is so sensitive, we can use very low excitation amplitudes and there is no risk of neither burning up the piezo nor damaging the sample. Now, as expected from the single frequency scans, we can see that the 2 larger delamination patches show up almost straight away. The smallest single-cell delamination, however, does not show up until we reach the highest frequencies around 80 kHz. This is also as expected, as the resolution needed to capture this tiny defect is only present at the higher frequencies. To increase the sensitivity to smaller defects like this, we can both increase the amplitude of the excitation and also run repeated scans. But in this case, this isn't needed as it shows up quite clearly in the initial damage detection scan. Oh, and in case you wondered, Optonor won that benchmark test. If you're curious about what more our instruments can do, please don't hesitate to get in touch.